Thank you, Mr. Chairman. My name is Takeshi Yasui in Tokushima University. Today, I will present the combination of dual-cone spectroscopy with Jones matrix polarimetry, namely Jones matrix dual-cone spectroscopic polarimetry, or JMDC-SP. Go to background. The spectroscopic polarimetry, or SP, is a technique that combines the polarimetry and the spectroscopy to analyze the polarization property of light as a function of wavelengths or optical frequency. So measuring such a polarization property with respect to the wavelengths gives variable information of a sample. The SP is widely used in the thin film evaluation of silicon wafer, visualization of stress distribution, and biosensing applications. In conventional SPs, optical spectrum of broadband light is acquired while modulating the polarization or phase of the input or output light, like here. But a mechanical modulation often limits the precision and acquisition rate. Although the phase modulation type can achieve the rapid measurement, but the phase modulator is not stable for the broadband polarimetry. In this way, the polarization or phase modulation limits the performance of the conventional SP system. Recently, the dual-cone spectroscopic polarimetry, or DCSP, has appeared as a new approach for SP based on the optical frequency cone. So this here shows a typical configuration of the DCSP, so which is similar to the DC dual-cone spectroscopy, or DCS. A key difference between them is the detection part, including polarizer and a pair of photodetector. So use of the DCS in SP enables able to acquire the high-resolution optical spectra of amplitude and phase without the need for the mechanical time-delay scanning. Furthermore, the simultaneous acquisition of the optical amplitude and phase spectra for X and Y polarization gives the optical spectrum of phase difference delta and amplitude ratio of psi between the X and Y polarization, without the need for the polarization modulation. Therefore, the DCSP can work as a modulation-free SP. So for further enhanced performance of DCSP, what additional functionality is necessary? One representative candidate is the Jones matrix, because the Jones matrix enables more detailed analysis of optical property of a sample. So in Jones matrix or JM polarimetry, one analyze the polarization of the output light from the sample, or assuming the polarization of the input light is known. And then, so based on the calculation of Jones calculus, this calculation, the Jones matrix of a sample is calculated from the Jones vector of the input polarized light having a known value, and the Jones vector of the output polarized light having a measured value. However, the Jones matrix includes 4 unknown parameters, including J00, J01, and J11, and J11. So the so in this case, so the multiplexing of the input polarized light and corresponding measurement of the output polarized light are required, like here. How so we can multiplex the input polarized light and the corresponding measurement in DCSP? The answer is given by a polarization control pulse sequence, PCPS, which is a time-domain multiplexing of the polarization. For the generation of PCPS, a single OFC pulse is divided by first PCP and second PCP by beam splitter. The first PCP maintains the same polarization of the horizontally linear polarization, whereas the second PCP changes the polarization and time delay using another optical path. And then so they are combined again, having a different polarization and time delay. Finally, by adjusting the half-wave plate, we obtain the PCSP composed of the first PCP having a linear polarization directed at the 45 degree and the second PCP having a linear polarization at 135 degree with a time delay of delta tau. So the DCSP or PCPS enables a JMDCSP without the need for the polarization modulation. Next slide shows a schematic drawing of experimental setup of the JMDCSP. So here is optical setup for the generation of PCPS. The after the PCPS passes the sample, we further multiplex and one additional OFC pulse having a linear polarization directed at 45 degree as the reference pulse. And then they are combined again by beam splitter. So the three sequence of the PCPS of the OFC pulse having a different polarization and different time delay is interfere with the local OFC beam to generate an interferogram. This results in generation of three sequences of interferogram between them. And then, so X and Y polarization component was separately detected by a pair of photodiode and PBS. And then, so we after separating each interferogram individually, we perform the Fourier transform of them to obtain the optical spectra of amplitude and phase for X and Y polarization. Next slide shows the calculation procedure. First, the Jones vector of input PCPS given by J1 and J2, which having a known value. And the second is a Jones vector of output PCPS measured as J1 dash and J2 dash. And finally, the Jones matrix of a sample is calculated from this equation by substituting the Jones vector of input PCPS and Jones vector of output PCPS. We first investigate the basic performance of PCPS. Upper graph shows a temporal waveform of the three sequence of interferogram for X and Y polarization. We clearly confirm the three sequence of interferogram for as the first PCP, second PCP, and reference pulse. Next, we place a linear polarizer directed at the 45 degree at the sample position. In this case, second DC PCP is disappear due to the blocking of the polarizer, and the first PCP and reference pulse were observed for X and Y polarization component. On the other hand, if the polarizer is directed at the 135 degree, the first PCP disappear and the second PCP and reference are observed. In this way, we confirm the validity of the polarization for the PCPS. Then we obtain the optical spectra of JM components, so J00, J01, J10, and J11 composed of the real and imaginary part. So that in this graph, the black plot shows the experimental data and red plot shows the theoretical curve. The first sample is zero order quarter wave plate directed at 130 degree. And a theoretical value of the Jones matrix is given by this equation, composed of the Jones matrix of quarter wavelet and coordinate transformation of the optics rotation. like here. So from the experimental result were in good agreement with the theoretical value for each JM component. Next, we rotate the same quarter wave plate to be directed at the 90 degree. So in this case, we adjusted the coordinate transformation matrix. So in this case, we confirm the angle dependence on J11R and J11I between the zero order quarter plate directed at the 90 degree and 130 degree. So this one and this one, okay, like here. And the next sample is a multi-order quarter wave plate directed at the 90 degree. So compare with zero-order quarter wave plate, the multi-order quarter plate enhance the phase retardation, this part. So in this case, we confirm the enhanced wavelength dependence on J11R and J11I compared with the previous result here, like here. And the next sample is a Faraday rotator having an optical rotation angle of plus 45 degree. So the theoretical value of the Jones matrix for Faraday rotator is given by this equation, which is independent of the sample of the rotation. So in this case, we don't confirm the angle dependence on all JM component. The result is not shown. And finally, so we place the pair of the zero-order quarter wave plate and the Faraday rotator in series. The theoretical value for the combined Jones matrix is given by this one, and the experimental data is good agreement with the product of James spectra in zero-order quarter plate and Faraday rotator. In this way, we confirm the validity of the JMDCSP for the polarization optical component having a non-polarization property. Finally, we summarize the present talk using this slide. Thank you for your kind attention.